Good morning, everyone. Okay, welcome on the fourth day of Ignite. Thanks for coming. My name is Jakub Szymaszek. I'm Program Manager and SQL team. I work on security features for SQL Server and Azure SQL Database. And with me, I have Dean Wells. He's a PM in Windows Server-Based team. He works on security features in Windows. So in this session, we're gonna share with you information about some exciting and truly game-changing, we believe, data protection technologies that we are introducing in the SQL platform by leveraging what is called the secure enclave technology and a bunch of other technologies that Dean's team has been working on in Windows. So that's why I invited Dean so that he can present to you the Windows part of our end-to-end solution, okay? So let me kick it off by giving you some context here about the problems that we are trying to solve with the technology called Always Encrypted in SQL. So many of you are probably familiar and are even using techniques, mechanisms, features for protecting sensitive data in database systems in SQL, in particular, at rest and in transit. So we have fairly mature technologies that protect data at rest, protect data in transit. Transfer and database encryption is a prime example of that. There's a technology that existed in the SQL Server for about 10 years or more. We have TLS, SSL that is also supported in SQL Server for protecting sensitive data in transit. So now the challenge is that the protection that TD provides, it ends the moment your data is loaded back from disk into memory, right? The protection that TLS or SSL provide ends at the moment your database server receives data from your application, right? And after that, the data appears in memory of SQL Server processes in plaintext, right? So the problem is that until recently, what was missing was mechanisms to protect sensitive data in use. By that, we mean data that is used in memory of the database system during query processing. And that's exactly the problem that Always Encrypted technology that we introduced a couple of years ago is attempt to solve, right? Let's double click on that. So the challenge, the issue that we are trying to address is how to protect sensitive data inside the SQL Server environment from powerful adversaries, basically high privilege but unauthorized users. That includes database administrators, administrators of machines hosting SQL Server, cloud operators, or any malicious process that may have infected the hosting machine, the environment that hosts your database, right? Now, the challenge is that it's relatively easy to achieve protection of sensitive data in use if this is just your only goal, right? You can basically ensure that the data that you store in the database gets encrypted before it is stored in the database using your favorite encryption algorithm like AES-256, for example. The challenge is that once you do that, you have compromised the query processing capabilities of your database environment. And SQL Server or any database system will not be able to perform computations on your data, process your queries, right? So that's what we don't want. So ideally, our goal is to achieve what we call confidential computing or computations without seeing the data. We want SQL Server process to be able to perform rich computations on the data, pattern matching, arithmetical operations, whatever you can think of, sorting, ordering, and so on, in such a way that the data is never ever exposed in plaintext to the potential attackers in the server environment. So that's the challenge that we are trying to solve here. So as you can see, we're trying to achieve two goals that are until recently have been kind of mutually exclusive and not achievable together. And on one side, protecting sensitive data in use from these powerful adversaries. On the other hand, ensuring that the SQL Server can continue support rich functionality of SQL queries, okay? So about 2 years ago, we've made the first step towards this vision. Okay? And this first step was the release of the first version of Always Encrypted in SQL Server 2016. So how many of you are using or are familiar with Always Encrypted that we shipped in 2000? Okay, quite a few hands. So let me make sure that we are on the same page, because I want to, we need to understand the mechanics of this Always Encrypted workflow and technology, so that we can dive into how enclaves enhance it. Okay? So Always Encrypted is a client-side encryption. It works by encrypting, decrypting data on the client side, right? So what this means that, as you can see in this diagram, the data appears in plaintext on the client side. The client application owns the data, but the moment the data leaves the client application, the data gets encrypted. Okay? So the SQL Server never sees the data in plaintext. It doesn't see the keys that were used to encrypt the data in plaintext either, right? So this client-side encryption has two other important properties. One is encryption transparency. So this encryption decryption happens inside a client driver, ADO.NET, ODBC, JDBC, and that client driver transparently encrypts, decrypts data. It figures out transparently which data needs to be encrypted before it is sent to the database, and which query results need to be decrypted. So the application doesn't have to call crypto routines explicitly to trigger these crypto operations. So that makes programming and app development easier. The other key property that, as I mentioned earlier, this initial version of Always Encrypted was the first step towards achieving the confidential computing vision, right? So in this initial version, we managed to support some operations on encrypted data. To be precise, it is just one type of computation, namely equality comparison. And we achieve that by using what we call deterministic encryption. So deterministic encryption is a type of property-preserving encryption, which ensures that if you have two values that are equal, two plaintext values, after encrypting those values, the resulting ciphertext values are also equal, right? So what this means is that SQL Server now then can reason, can deduce that two plaintext values are the same by comparing their ciphertext, doesn't have to know the underlying plaintext, right? So this is very basic and very simple, but surprisingly in database systems in SQL, there are quite a few types of queries that leverage just equality comparison that are quite useful. So point lookup searches are one example, equality joins another example. We also can support simple aggregations using group by operations, okay? So that's what we did about 2 years ago, and that was our first step towards this confidential computing vision. Now, let me double-click and spend a few minutes on this architecture that exists today, which we're going to build on top of to support more functionality with secure enclaves. So Always Encrypted is as those of you who used it know, is a column-level encryption. So you choose individual columns to be encrypted, and they are encrypted with what we call column encryption keys. These are symmetric keys, which are protected with asymmetric keys that are called column master keys. And it's a many-to-many relationship. You can have many columns, many keys, right? Now, the important thing to know is that neither keys are visible to the database system, right? So you have column master keys, which are stored in the encrypted form in the database metadata, never in plaintext. And you have master keys that are under control of the application. So the application is responsible for managing those keys, and we support out of the box the ability to store those keys in Windows Certificate Store, Azure Key Vault, HSM devices. So you can also choose to store them in a custom key store, right? Now, let me walk you through the typical query processing workflow for Always Encrypted. So in this example, on the right-hand side, you can see a table with 2 columns encrypted. On the left-hand side, you have a client application that is trying to issue a point lookup query, right? So we're looking for a matching name for a given social security number, which is a government ID in the US. These 2 columns are encrypted on the server side, right? So the first thing that normally would happen in this case, the client driver, after receiving this query, would just send it to the SQL server, submit it for processing, right? Now, with Always Encrypted in place, instead, the client driver will make transparently this metadata discovery call by calling the store procedure called SP-describe parameter encryption. So what is happening here, the driver submits the query statement that was invoked by the application, and the SQL server analyzes the statement, parses it and analyzes it to figure out which parameters, query parameters in the statement need to be encrypted on the client side. So basically, it concludes in this case that the @SSN parameter in this query happens to correspond to the database column, SSN, which is encrypted. So what it does, it responds with all the metadata, all the information it knows on how this column is encrypted. So this is the key part. Somehow, the way to describe Always Encrypted is to say that this is an encryption technology that is informed by server-side metadata. Client-side encryption informed, controlled by server-side metadata. So the server knows about which columns are encrypted, how they are encrypted, and it supplies this information dynamically to the driver, so the driver now knows what to do. So the first objective of the driver in this workflow is to decrypt the column encryption key that is stored in the encrypted form on the server side and then send back in this response to the client. So the client knows where the master key is from the field that is called here column master key path. So it reaches out to the key store, calls the unwrap operation, decrypt operation on the key store. Now it has a column encryption key, data encryption key in plaintext. And what it can do, it can now encrypt that query parameter, that SSN value, rewrite the query statement, not the query statement, but the query invocation, and replace the plaintext with the ciphertext. So what the server gets is ciphertext of the query parameter that corresponds to the encrypted column. And assuming that the SSN column is encrypted using deterministic encryption, SQL Server can evaluate this equality comparison in the workflows, right? So that's what I mentioned earlier. That's how we support equality comparison via deterministic encryption. So now the SQL Server found the matching name. It knows that this value comes from the encrypted column, and therefore it attaches, again, all the metadata that informs the client how this column is encrypted, which allows it this time to decrypt the name value from the result set, presenting plaintext to the application, right? So what you get here, two kind of main takeaways from this slide. All this complication workflow that you see on the right-hand side of this diagram, all this complexity is hidden from the application point of view, right? It sends a query submitting plaintext data and receives a plaintext response, a plaintext result set. That's one key point. The other thing is that because of deterministic encryption, we can support some types of queries like equality comparison in point lookup searches. So that's how it works today. You have a question? Right, so the question is, how will SQL Server know which data should be encrypted? So I'll show you that to you in a demo in a second. Basically, when you define, this is part of your table schema. So your table schema contains the information about which columns are encrypted and how they are encrypted. So when you define the schema, you would designate some columns as encrypted, okay? So that's what we have today. Now, You may say, okay, equality comparison, that's great. I can do point lookup searches. I can do equality joins. Well, for many applications, and we got this feedback from customers and kind of knew that upfront at the time we even shipped this initial version of Always Encrypted, equality comparison is not sufficient for many types of applications, right? If you have an application that processes, for example, rich personally identifiable information, like names, addresses, phone numbers, and so on, there is a chance you want to do more than equality comparison. You may want to do point lookup searches or sort these values, or you may want to perform arithmetical computations on some sensitive numerical data, right? To achieve that today with Always Encrypted, the current version of any other encryption technology that protects data and use, in fact, you would have to modify extensively your applications so that they pull all the data from the database and re-implement your business logic on the client side. And if you have a sufficiently large data set, they will just not scale, right? It will be extremely hard for you to achieve that. So that's what I meant earlier when I said that achieving these two goals, protecting sensitive data and use on one side and preserving an ability to perform rich computations, that's something that is very hard. So that's one problem. The second problem is more on the operational side. For those of you who use Always Encrypted in SQL Server 2016, 17, or Azure SQL Database, you know that in order to perform any cryptographic operations on the data, for example, to encrypt your data for the first time, or to rotate column encryption keys, right? You have to move all your data outside of the database again, perform these operations on a different machine, and then upload the data back. SQL Server cannot perform these operations for you by design because it doesn't have access to the keys, right? So that's, again, is challenging both from performance reasons, also from the compliance, security reasons. Now you need to have this other machine that is part of your compliance security domain, which can safely access encrypted plaintext data, in fact, and encrypt or re-encrypt them, right? So these are main two challenges that we are trying to solve. And the technology that we'll use to tackle these hard problems is called secure enclaves. So let me spend a few minutes explaining what enclaves are. How many of you actually have heard about technologies like Intel SGX? Okay, a few, all right. So an enclave is a special region of memory. It's an isolated, protected region of memory, which is, of course, part of a containing process, and it has some really cool special properties, right? Namely, it is basically not accessible to not just to the containing process, but everything else on this machine, all other processes and the OS itself. So basically, it's a black box that cannot be accessed by administrators, operating system, other processes, or the containing process on that machine, okay? And it runs, may contain, of course, code and data, and that code needs to be signed in a special way to run inside the enclave. Now, there are several ways to achieve enclave isolation, to protect the enclave memory, and different technologies achieve that in a different way. We can categorize them in general in two buckets. So some of them are hardware technologies, and Intel SGX or ARM Trust Zone are examples of those. So in the case of hardware technologies, the isolation of the hardware or of the enclave is provided by, in case of Intel SGX, for example, by the CPU itself, and the enclave memory is encrypted. And it's therefore the data in it, the code in it are not visible for anything else on the machine. The other technology or the other types of technologies leverage a hypervisor on the machine. And in this case, a hypervisor is the entity that guarantees the security and the isolation of the enclave. And virtualization based security enclaves in Windows are example of this approach. So to give you an idea what the experience would be if you try to access the memory of a VBS enclave. This is a screenshot that I took when after I opened a WinDBG debugger, and I connected to a process that contained the enclave, and I found the enclave memory, right? So I was pretending to be an attacker that wants to exfiltrate the data from the enclave, right? So this is what I could see, the question marks. I was not able to see the actual data. So if you perform a memory scanning attack, you won't be able to see the enclave memory. If you take the memory dump, you won't find the enclave memory in the dump, right? So these are key properties of enclaves that make them very attractive technology to serve as trusted execution environments for processing sensitive information. Okay? So that's exactly what we are using in the upcoming version of Always Encrypted, called Always Encrypted with Secure Enclaves. We're actually very excited about SQL Server 2019, which was announced earlier this week. There is a public preview of SQL Server 2019 already available to you, and it does include Always Encrypted with Secure Enclaves. We use VBS enclaves in the current version, so you can now, all of you can now see and try and test it. So from the security standpoint, the goal of Always Encrypted with Secure Enclaves doesn't change. The goal is still to protect sensitive data from high privilege but unauthorized users, okay? You don't want DBAs, machine admins, and so on to see the data. What we want to improve on is functionality. So we want to preserve SQL Server ability to process rich queries, and we want to support in-place encryption so that you don't have to move your data outside of the database, right? So this is how we're gonna do that. So we have modified SQL Server so that when it starts, it loads a VBS enclave. So a SQL Server now is a hosting process that contains an enclave, right? And this enclave runs the code that is responsible for evaluating certain expressions in SQL queries, okay? So, and this enclave essentially acts as an extension of the client on the server side. You can think of it as a trusted representative of the client application within the SQL Server environment. It's like an ally behind enemy lines, or like a foreign office in a given country, right? It's an extension of the client-side trust boundary. And the way we use the enclave is during query processing, SQL Server delegates certain operations to the enclave that now, being a trusted execution environment, can safely decrypt the data and perform computations on plaintext. So that opens up new possibilities. We can support, in general, all kinds of queries. We're starting with a few that some of you and other customers have asked for, and that's our top priority. So we want to support in the current version, in the current preview version of SQL Server 2019, we support rich queries like predicates, pattern matching, range queries. We're still working on indexing, and I can tell you more about our roadmap in the next slide, in one of the next slides, our roadmap for the next milestone, next releases. And one more thing that gives you is in-place encryption, right? So with enclaves, we can also delegate cryptographic operations to the enclave. So you don't have to move your data and use tools like Always Encrypted Wizard or PowerShell that run on the client side. The enclave can perform these cryptographic operations for you locally, securely inside SQL Server. There is a question. That's right. Yeah, so we'll talk about it more. I'll repeat the question. The question is, are there any specific requirements regarding the version of Windows or hardware? So yes, there are specific requirements regarding, in general, I think the correct answer is both, but Dean can elaborate on that when he talks about attestation. This technology is available in the latest version of Windows, Windows Server 2019, and its client counterpart, which is called the Windows 10 version 1809, if I'm not mistaken. Okay. And regarding hardware, we'll talk about it. We'll recommend that your machine is equipped with TPM 2.0 for production purposes. You don't have to have it for testing. We'll get there, okay? Right. The question is, what's the cardinality of relationship between enclave and SQL Server? So SQL Server contains just one enclave. The enclave is stateless. So not quite stateless, but it contains information about sessions. I'll get to that in a second. But it's one per SQL Server process. Okay? All right. So I just told you that this enclave is responsible for processing sensitive data and is capable of decrypting sensitive data and can operate on sensitive data on plaintext, right? So, and it's basically, and the assumption here is that the enclave is an extension of the client-side trust boundary, that the client can trust the enclave, that this enclave is a trusted friend of the client application. But how do you know, and how does the application know that that's true, that this enclave is a trusted friend, not an enemy, right? That this enclave doesn't run perhaps a malicious code that publishes your sensitive data on a file share or to the internet directly or indirectly, right? So that challenge, that problem is addressed by what we call enclave attestation, which typically involves the client application or an SQL server interact with an external service called an attestation service. And the role of the attestation service is to certify, to prove to the client before it attempts to use the enclave, before it authorizes the use of the enclave. It proves to the client that the enclave is trustworthy. It's a real VBS or SGX enclave, for example, and it runs the code that you can trust. And Dean will spend about 15 minutes to talk about that after I do my demo in a moment, okay? So that's one common question that pops up. The other question you might be thinking about is, okay, so I just told you that SQL Server never has keys in plaintext, right? And I also told you that the enclave inside SQL Server decrypts the data, right? Or re-encrypts data. So the question is, how does the enclave get the keys if it's part of the SQL Server process, but SQL doesn't have the keys in plaintext? So this challenge is addressed by the client driver creating a secure tunnel or a secure connection, a secure session to the enclave. So this is done transparently during normal connection setup process using TDS protocol, which we have enhanced. So during that part, basically the client and the enclave negotiate a shared secret using Diffie-Hellman protocol, and now they have a shared secret that they can use to, that the client can use to encrypt column encryption keys that can now be securely passed to the enclave, so the enclave can perform cryptographic operations on the data. And the client also signs queries so that we have guarantees that only properly signed queries can be executed inside the enclave. So there are some security in-depth protection that we have added as well, okay? So with that, let me show you a demo of what is available today in SQL Server 2019, okay? Right. So the question is how much RAM is allocated to the enclave. So one way to answer your question is that, so today in SQL, we don't allocate a specific amount of memory. We kind of let the enclave grow dynamically. With VBS enclaves, that's very easy. there is no limit for the size of the VBS enclave. With SGX, there are much stricter, or the limitations regarding memory size exist. But even with SGX, we can work with fairly small enclaves. So the size is not an issue. With VBS, it's not an issue because there is no limitation, in fact. Okay. All right. Which number am I here? 4, I think. Okay, I guess I'm not connected. Sorry about that. All right. So for this demo, I'm going to use a very simple data set. It has just one database with one table. So let's see what this table contains. It contains some information about employees, social security numbers, and salary figures is the sensitive information in that table. And right now, I'm wearing a hat of a database administrator. I can see all the data in plaintext without any issues, right? If I'm a machine admin on this machine, or if I'm malware, I have even more means and ways to exfiltrate the data. I can scan memory, I can generate a dump file, and all that data will be there in plaintext, right? So that's the starting point for this demo. Now, I also have a web application, which is a very basic .NET app that displays all this data. And in addition to that, it allows me to do some filtering. So I can filter these employees by salary range, or I can filter them by a portion of a social security number. And now let's see, if I use this application, at any point of time, it triggers a SQL query. So let's see how this query looks like from the SQL Server point of view. So this is what SQL Server gets, right? As you can see, it's a fairly rich query. It contains a like predicate on the SSN column, range comparison on the salary column, right? So this is the goal for this demo. I want to protect my sensitive data in use. I want to make sure that high privileged but unauthorized users like DBAs on the server machine cannot access my sensitive data in plaintext, but I want to do that in such a way that allows me to keep this application unchanged, right? I want this particular query to continue to run in the unchanged form, okay? So that's the goal. I don't want to re-engineer my app, to load the data, replicate this computation on the application side, okay? So let's do that, and we'll do that by configuring Always Encrypted using enclaves for this particular table. So the first step for you to use Always Encrypted, I'm skipping the setup part, which is not that exciting here. So there is a bunch of OS level configuration that you need to do, and Dean and I will talk about it later on. But after you've set it up, the first step you would do in SQL Server is you would create a column master key, right? This is the key protector that we use in Always Encrypted. I actually have already created a master key. It's a certificate in the local machine store on this machine. So what I'm doing now, I'm basically creating a metadata object inside SQL Server that describes, references this master key, which is a certificate. So let me do that. And there is one little detail I want to highlight here. So this allow enclave computation checkbox. I check it, I select it to express my intention, which is I want column encryption keys that will be protected with this key protector, with this master key, to be permitted to be used inside enclave computations, okay? So let's do that. Let's complete this dialog. So I can briefly show you what this did to the database. So this is the script for creating the metadata object I just created using this UI. As you can see, there is this enclave computations property, and there is also signature that was dynamically generated by this tool. It prevents all that metadata, including this property, from tampering, so that if you don't want, as a data owner, for your data to be used in enclave computations, you have a mechanism to enforce it, right? So that signature achieves that, okay? So we have a column master key. What else do we need? We need column encryption key, right, to encrypt our data. So let's again name the metadata object that is describing it. Let's click OK. Multiple things happened when I clicked OK. The plaintext CK got generated. It was encrypted, got encrypted with the master key, and uploaded as a metadata object to the database. Okay. So now I have a key pair. Let me try to encrypt them. So now, for those of you who are familiar with the current version of Always Encrypted, what would you do to encrypt your data? What do you do? Which tools do you use? What's your favorite tool? You have two to pick from. SSIS is one option, so maybe more than two. Always Encrypted Wizard and SQL Server Management Studio or PowerShell. So with Always Encrypted Wizard, you would basically go here and open encrypt columns, and you would complete this wizard at the end that would trigger time-consuming and expensive data migration operation. It would move all the data from the database, encrypt it, upload it back. We don't want that, right? Instead, we want to encrypt this data in place, and with the changes we have done in SQL Server 2019, you can do these operations using plain, boring, alter table, alter column syntax. You can do all that in T-SQL. There is one condition, however. Now you're acting as an owner of the data, right? So, which means that you'll be encrypting it, and that means that you need to have access to the keys, right? So there are certain conditions that you need to meet. So you need to run this operation from the machine that has access to the master key. In addition, you need to ensure that you Always Encrypted is enabled in the database connection, and that you specify the endpoint of the attestation service that will be used to verify the enclave before in-place encryption actually happens, okay? So again, that's something that we'll elaborate after the demo, okay? So let's run this script, okay? So it's completed instantly, partly because I have a very small data set, but mainly because all this operation, this cryptographic encryption operation happened locally inside SQL Server. No data movement was involved, right? So how do we know that the data actually was encrypted? So now back to my first query window. You can see the previous results of it, right? So let me now rerun it, okay? So now, as a DBA, I can only see SSN and salary values encrypted, right? And sure, if I change my connection properties, and if I specify, this flag for this query window, I will be able to decrypt the data, but only because I have the master key on this machine. If I do the same thing on a machine that doesn't have the master key, I will get the failure. I will not be able to get access to plaintext, okay? So now we have the data encrypted. Let's see how our web application got impacted by putting encryption in place inside the database. So let me refresh this up. So as you can see, it still shows data. It actually shows the SSN and salary columns in plaintext. And this is because this application has been already pre-configured with these connection properties that I showed you in SSMS. So Always Encrypted is enabled in the database connection. So what it does, it turns transparent decryption on in this case. The results that are retrieved in the encrypted form, the driver transparently decrypts them and shows plaintext to the application, right? So that's why the application can see the data in plaintext, because it has access to the keys, okay? But not only that, the most important detail here is that these filtering capabilities, filtering by salaries, filtering by social security number, portion of it, still work, right? So let's see if and how the queries, these application issues have changed. So I will go back to my extended event session, and I will show you how the query that SQL Server gets looks like now, okay? So 2 things to note here. No change to the query statement. This is the same rich query that you saw before. Despite the fact that my 2 columns are encrypted now, and SQL Server doesn't have access to the untrusted portion of it, doesn't have access to plaintext, it can process it, right? The second thing to note is that these search criteria, query parameters, the SQL Server gets them in the encrypted form now. Because again, the usual always encrypted workflow kicks in, and it causes these salary, min, max, SS and pattern parameters to be transparently encrypted inside the client driver. So the SQL Server gets parameters in the encrypted form, has the data stored in the employees table in the encrypted form. It sends this data to the enclave. The enclave safely decrypts the data and can perform comparisons or a pattern matching on plaintext. So that's how it works. So what I achieved is I managed to protect sensitive data in use from high-privileged users, and at the same time, I've done that without changing my application queries. I didn't have to re-engineer my application to load the data and perform computations locally, okay? So now, as we said earlier, all that works with the assumption that this enclave is a trusted entity, okay? That it's a trusted representative of the client application on the server side. So now, how do we know that that's truly the case, okay? How does the application get this assurance? So now Dean and I will walk you through the workflow of attesting the enclave, maybe after you explain what AGS is and how it works.
Sounds like a plan. All right, hello everybody. So what we're talking about here is, this is a service whose purpose in life is become a role in Windows. It's been there since Server 2016, and it's been matured in Server 2019. And its purpose in life is to sit in a physically secure data center somewhere and attest to the health of other workloads. The process of attestation is I take measurements from something, typically they are cryptographic measurements, and then I compare them against a pre-configured whitelisted policy, and that gives me the ability to say healthy or unhealthy. That's basically what the Host Guardian service does. Now, it does it currently for precisely 2 workloads. The first is for Hyper-V. We use it for a technology that I also own called shielded VMs, and we use it for SQL Always Encrypted with enclaves. So we expect this model to mature. Right now, it's a Microsoft-only thing. We will eventually expose it so other people can write enclave binaries and leverage this trusted execution environment. But for now, it's a Microsoft-only thing. The reason it's Microsoft-only is because we haven't yet built like a code signing portal or ways of figuring out if the binary should even be signed. Because I don't really want somebody writing a binary that's got a built-in virus, us then signing it in a code signing portal, and somebody giving it implicit trust because it runs inside an enclave. So we've got some work to do now that the technology is working for us to ensure that we can offer this to third parties. So you now know what the process of attestation looks like. I want to tell you exactly how it works. Now, with my regular audience, I tend to get a room full of IT security geeks. My suspicion here is I don't have a room full of IT security geeks. I have a room full of DBA geeks, would be my guess. So what I'm going to do is wow you with science you may not understand, but hopefully you'll walk out of this room saying, this isn't security theater, this is genuinely strong security controls put in place by Windows to prevent malicious software or even admins running on a host where the data physically resides with them from even getting into that data. That's the goal. So how do we identify a SQL host that is legitimately allowed to process this database, decrypt keys? How do we do that? Could we identify it by a name or a serial number on the motherboard or an Active Directory domain join account? We could use all of the above. What we chose to use was something extremely strong. We chose to use the TPM. Who's heard of the term TPM? Okay, that is most of you, great. So a TPM is a trusted platform module. It is a tiny little microchip that runs typically on the motherboard of most PCs these days. It runs in laptops and in servers, and it is used as a way of securely sealing keys. Sealing's an interesting term, and I use it very deliberately. It's keys, secrets, anything really, but it's typically very small pieces of data, so oftentimes the secret is a key or a password. The process of sealing goes like this, and this is where we get a little bit deep, so we'll do it relatively slowly, and feel free to ask questions as I go through this if it's relevant. But again, this isn't massively important that you understand how it works end to end, but it's cool to understand the security assurance strength that comes from it. When a PC boots these days, you've got two BIOSes that you could choose from. The old one is called PCAT or PCAT BIOS. That's what we used to use years ago. The way that would boot is the machine would be powered on with the big red switch. It would read the BIOS off of a ROM. It would run that BIOS. That BIOS would eventually finish setting up the hardware, and it would then go and look for the first boot device based upon the controllers and the disks it's using. It would then go to a logical sector of about 512 bytes in length, read it, and then without any regard for what it said, run it. That sounds incredibly secure and difficult to attack, doesn't it? That's the way things used to work. And that was very, very easy to insert a rootkit because all you had to do was change that first 512-byte sector, make it go and run your component that got into the computer first. It then went back to the original sector that it had moved, and then the rest of the operating system loaded with this nasty little rootkit looking up at it going, I can see everything you do and you don't know I'm here. That's the purpose of a rootkit. That's how they work. They get there first, and then everything else doesn't realize they're there while it looks and inspects everything they're doing. That's the past. It doesn't work that way anymore. The reason I'm pointing this out, though, is because a lot of machines still ship from vendors today with support for both types of firmware. PCAT, the PCAT one I just described, or UEFI, the Unified Extensible Firmware Interface. UEFI is the new one. A lot of machines switch with PCAT or PCAT switched on, and you have to turn on UEFI. For this particular feature to function, you need UEFI firmware. The gentleman here-ish, I believe, asked a question about the hardware requirement, or was that you? I don't remember which. That was you? Somebody, yeah. So you need UEFI firmware for one. You need a TPM v2. TPM 1.2 is simply something that we could have supported, but we chose not to. The reason we chose not to is we would have had to rewrite the entire attestation mechanism for each version of the TPM. So when the variant causes that much work, and the version we're going to support is the later and greater one, it makes sense for us to not look to the past. So this was quite literally resourcing. We could have done it with the TPM 1.2. We didn't. We did it with what's more modern, more secure. You also need some very specific technologies in the platform, typically referred to as VTX or virtualization extensions. Most machines that you would buy that you would run SQL Server on these days will have that support for free. In many cases, though, it's not switched on. So you would actually have to go into the firmware and potentially switch on Intel virtualization extensions, which is what VTX stands for. The reason we're doing this is because the entire technology that Jakob described earlier on, the trusted execution environment, the enclave, it's achieved by using the same technology that Hyper-V and VMware and Citrix Xen and Amazon and Azure use to keep an isolation barrier between two VMs. It's exactly the same technology as that. It's no different at all. So instead of guaranteeing that VM1 can't inspect VM2 and vice versa and so on, we guarantee that we can compartmentalize and isolate the operating system components such that this tiny little TEE, Trusted Execution Environment, can live quite safely, and even kernel mode components in a legitimately booted scenario can't see inside it. Even the kernel can't get in there. And that's one of the key things that people struggle to take away. The kernel is not the master of this system anymore. The hypervisor is. So the question then becomes, if I've got UEFI, I've got TPM, I've got VTX, and I've got Windows, and I've just said that even the kernel can't get in there, well, I could argue that, well, the kernel can get in there. What if the machine's not being measured? What if it's not got an attestation authority? Now if somebody breaks our software model, and they manage to get something in before the hypervisor, now everything I've just said is rendered moot. So what was the point of building it all? Well, the point was we have to have that to implement it in software and to implement it in today's hardware, but we need to make sure it's running as it was designed. That's where attestation comes in. SQL's doing all this magic, all this stuff going on with VBS enclaves. Windows Server 2019 is using all these very clever virtualization security extensions to make this trustworthy execution environment exist, and somebody circumvented all of it by installing a rootkit. Well, we can't detect the rootkit unless somebody's looking for it, unless somebody's measuring it and knows what a definition of health looks like. That's where, again, the attestation process comes in. So first things first, we have out of the box, we've got SQL turned on. We've got UEFI firmware, we've got a TPM v2. All of those things happen, and you've got Windows Server 2019 installed. Now I want to make that machine work with a host guardian service so we can attest it as healthy. The first thing I do is I extract a key from the TPM. It's called an endorsement key. Every TPM out there has an endorsement key, a public and a private key pair. We extract the public version, and we use that as the identifier. So we ship the public key from the TPM over to the host guardian service. This is not like a shared secret. This is typical asymmetric cryptography where one key can be used to encrypt and the other key can be used to decrypt. And for those of you who aren't familiar with it, it doesn't actually matter which way round you do that. If you encrypt it with the private key, then the public key can decrypt it. And there is actually a reason for that. We use that for signature purposes. But typically, the public key encrypts, the private key decrypts. Where do you think the private key resides? Forever and eternally inside the TPM. It will never release it. It will release data that it decrypted with that if it's deemed appropriate to do so, but it will never release the key. So when the machine needs to become registered with the host guardian service, one time and one time only, you extract the EK pub, the endorsement key public, from the TPM, and you give it to the host guardian service. What you've now achieved is you have identified a legitimate host. It is not yet blessed. What you now do is build the operating system on that host to the point where you consider it to be perfect. It is your golden image with SQL and with DB admin tools installed, anything that you want. You make a box that is built perfectly to your golden image. Please don't put, debuggers and malware and viruses on there, otherwise we'll consider those to be blessed because we're about to say that's trustworthy. So if you built it with a virus and then you tell the tool, deem this trustworthy, it will literally record the virus as being trustworthy. Okay, so build it with the perfect set of tools. You then run a process to go and scavenge all that information from it, and we record that information. The vast majority of what we are recording, isn't every single binary on the disk. It's those that constitute the boot path. And this is where I want you to understand how thorough this is. So when the machine boots up, UEFI firmware loads, and once it's finished initializing the hardware, it goes and looks in two databases. One is cleverly called DB. I suspect I've got far more chance of the people in this room defining what that abbreviation means than usual. It literally is database. They could have called it something a little bit more creative, but it's the database of goodness. What it is it's a secure variable inside the UEFI firmware that defines legitimate code signing certificates. So Microsoft's code signing cert is in there. Some of the Linux variations, SUSE and RHEL and all those, are in there. Then it's got another one called DBX, which is database excluded, which is the blacklist, if you like, of things that you should never load. And it can be either a hash of an OS loader or a code signing certificate of something that is allowed to boot the system. So as the system runs, the UEFI does its job, it initializes all that hardware, and it then goes to the disk that contains the OS loader. It reads the OS loader, then it compares the code signing signature and the hash to the DB variable. As long as it finds a match, then so far it's looking good. It then goes and does the same thing in the DBX to make sure it didn't find it there as well. If it found it in both, it will refuse to boot, and you'll get an error. If it found it in neither, it will refuse to boot, and you'll get an error. If it found it in DB, the system will boot. Make sense? This makes it very difficult to insert rootkits now, because even as people in the product group, Jakob can't get hold of the code signing cert for SQL any more than I can get hold of the code signing cert for the Windows Server operating system. We have operations and practices that prevent employees from doing that. That's all through automation. It's very, very difficult to subvert that process. There are far too many queues and monitors and physical processes in place to stop that from happening. So given that, if UEFI is trustworthy, which we have to believe it to be, there's not much we can do to say that it is or it isn't. We're working on technologies to make that the case, but we kind of have to trust the hardware, we kind of have to trust the TPM. So UEFI loads, it verifies the OS loader runs, and the process of booting the PC has started. Guess what the first binary knows? It knows the code signing certificate of the second. So when the first binary is loaded, we start measuring things. We measure the first and then the second. The first knew the signature of the second and would refuse to hand off to the second binary if the binary's signature had been tampered with. Make sense? So there's literally a chain here. So binary 1, which started from UFI, knows what binary 2 should look like. And binary 2 knows what binary 3 should look like. So there's our chain in the OS. In addition, we also measure the binaries by taking a hash. So here we go with some TPM terminology. We take the binary, we hash it, we store it into a register in the TPM. Binary 1 looks at binary 2. Binary 2 looks good. Hand control to binary 2. Now we hash binary 2, and we get a fixed size result again. We look at the hash that we just put in the PCR. We concatenate those two together, so now we've got a double-length hash. We hash it again and put it in the PCR. Now we go to binary 3. What do you think happens now? We repeat this ad nauseum right the way until the entire OS is booted. It's not far off, but it's not quite the same as blockchain because it's not as predictable, and you could obviously implement something in there, but you wouldn't be able to detect it retroactively. It would merely fail. But yeah, it's somewhat like a blockchain. These are called TPM measurements. TPMs work by sealing secrets to a set of measurements. So once the OS is up and running, imagine it was BitLocker, the file system encryption in Windows. The BitLocker full volume encryption key would be sealed to a set of PCRs that took certain measurements in a certain way. And the only time the TPM will ever release that key is if those measurements are exactly the same. This is how TPMs work. We do all of that in a host guardian service. So when that SQL machine comes up and it's doing all of the boot path for Windows and the enclave and everything else that you've blessed, it's generating a file called the TCG log, the Trustworthy Computing Group log file, at which point that is what we need to see how the machine booted and whether it's healthy. So SQL machine boots up, loads the UEFI firmware, loads control to the operating system, does the booting, does the PCR stuff, generates a TCG log, sends it to the host guardian service. Host guardian service compares it to a whitelist. Does this match? If it does, yes. Then it's all goodness, we think. But somebody could have lied. What if they recorded the TCG log off of the wire and then just threw it at me, and it was nothing to do with what they did? So what the host guardian service does is it runs through all of those operations again, calculates what the values in the PCR on the TPM should be, reaches back into the SQL host, compares the values in the PCR, compares them to what it just computed, and says, if they match, I now know who you are, I know you told me what you did, and I can now, with cryptographic certainty, state you actually did what you did. Last but not least, it looks for code integrity policies. Okay? That's what we're doing. All of that stuff happens every single time a SQL host needs to get sufficient health information back from a trustworthy host guardian service so that it can sign an enclave report and have a client be happy to talk to it and send keys over to it. That process happens in less than a millisecond. Sounds complex, but it's a PC. They're pretty powerful these days. So we have a variety of different attestation modes that you can use. The attestation mode I just described is the one at the bottom, the one with a nice big check mark next to it. That's the one that we recommend for production environments. The top one, Active Directory attestation, is being deprecated. As in, we don't want to keep that around, it's too complicated. We replaced it with something simpler. Host key. So your only two choices should really be, should I use host key or should I use TPM? If you're building a lab and you just want to see what SQL Always Encrypted with Enclave's performance is like, use host key mode. To attest the host, you literally go to the host, run one commandlet, ship a key up to the host guardian service, and run one other commandlet. It's about 3 commandlets in total, and now the machine is blessed. To do it with TPM, you have to get the EK-pub, you have to get the TCG log, you have to configure the policies, all of these different things. That's the work that you put into production environments long term. But if you just want to see what SQL looks like when it's running with enclaves, it doesn't make any difference how it was attested. The performance and the characteristics say the same. The only thing you lose by using host key mode is any guarantee of trustworthiness in the host. Go ahead. SGX and TPMs are somewhat unrelated. They're two security technologies. TPMs are simply used to measure things, whereas SGX is like our VBS enclave, but done in hardware instead of done in software. Question there is, do I have to have SGX as well as a TPM? You do not, no. If you want to going forward, which I'm not sure when SQL are going to release that, Jakob would know, but there is going to be a SQL enclave version of this as well. It will function with that going forward. Right now, VBS Enclaves is available on any host that meets the requirement I just gave you, which is pretty much any new host you buy from anywhere. Even your laptops would meet this bar. Okay, so use the host key mode if you just want to try SQL Always Encrypted with enclaves, because it doesn't affect anything to do with the performance. All it is about the trustworthiness of the device. Use the TPM mode when you want to do long-term production. So I give you a little bit of a breakdown here in terms of how each of them verifies whether or not the machine is healthy. And you'll notice that only the bottom one really makes an assertion of health. The rest make an assertion of identity. I know who the SQL host is because he's got the private key. I know who the SQL host is because he's domain joined and he's got this group. That's all we're doing with the top two. So they are more about recognizing somebody with some kind of cryptographic identity, but they are not strong enough because they don't measure the health of the host. And if you're going to be feeding keys into an enclave to decrypt very sensitive data, you need to recognize the health of the host. So I would urge that each of you take a look through these when you're building your proof of concept to make your choice, but I will strongly recommend your best practice for any production should be to ignore host key, ignore AD, that's being deprecated, it would be a bad idea, and use TPM trusted only. You can see here we talk about how measured boot is required. That was the TPM process I just described. Code integrity enforcement, that's kind of optional. You don't need to do that with a SQL host. It's far more important on Hyper-V. And then platform identity verification was the part where we extract the endorsement key from a TPM and use it as an identity. So last part for me is let's walk where Jakob will take on the role of the SQL client, the driver, and the SQL server, and I'll take on the role of being the host guardian service, and we will manually act out on stage looking like a pair of idiots exactly how this flow runs.
Right. All right, so actually I'll be playing collectively the role of the client and SQL server, okay? So on the client side, the first thing that happens, the application sends the query, right? And the client driver intercepted. As you saw in the previous animation. So the first thing the client driver will do after that, after getting the application query, and remember, this is the always encrypted scenario, right? So the first thing that will happen is the same call to discover the metadata about which parameters need to be encrypted and so on. But now in SQL Server 2019, we kind of overload this interaction. We add a new purpose to it, right? So this call, SP describe parameter encryption store procedure invocation, it also means the ask to SQL Server, give me a proof that the enclave you contain is trustworthy, that I can trust this enclave, that I can safely share the keys and use this enclave to perform computations on my sensitive data, right? So after that, what I would do as a SQL Server instance, I would call Dean and the host guardian service to request a host health certificate, right? So Dean, what is happening exactly in this stage, right?
So that is again then where we come back down to the attestation mode. The mode is what controls what happens next. If you do host key attestation because you want to try this in a lab and see what the performance characteristics are relative to non-encrypted or the previous versions of Always Encrypted, then I would recommend you simply use the host key. It will literally take you about 2 minutes per SQL host to set it up. It's that simple. If, however, you want to see what the characteristics are like when you're going through the real production environment, which obviously you would tend to do in a lab before you truly rolled it out, that's where this dance that you see here would be, give me a health certificate. No, I won't give you a health certificate. Tell me who you are. I am this EK pub. Look it up in my database. Yes, I recognize it. Generate a symmetric key. Encrypt it with a public key. Send it back to SQL host. SQL host passes it back down into VBS, uses the TPM to decrypt it. It's now got a symmetric key. We've got a shared key now. At which point, I'm going to ask it, give me your TCG log. It will then encrypt the TCG log and all that good stuff, send it back over to me. I decrypt it, compare it to the whitelist. Yep, you look good. Now I run through that TCG log, recompute what the values should look like in his TPM, reach back over that connection remotely into his TPM using a protocol we invented called RTPM, remote TPM, clever, huh? Mm-hmm. We reach back in, validate that the PCR measurements look exactly the same as what we've computed, and if they do, job done. Health certificate. We throw back a health certificate that contains a public signing key that was born on the machine inside our VBS enclave. It was born there. We send that back inside the health certificate, and Jakob now has exactly what he needs to proceed.
Right. So the SQL got the host health certificate at this point, which was signed by AGS, Host Guardian Service. The next thing it does, it calls a local Windows API to get what is called an enclave report. And an enclave report contains a bunch of information about the enclave itself and what's in it. What is the DLL or code that is running inside the enclave. And now this information is provided back to SQL client as a proof. So what follows is client's verification of that proof. So the first thing that client would do, it would reach out to Host Guardian Service, and this is why we specify this URL now in the connection string and when we interact with the database in SSMS. This is the endpoint of the attestation service that the client driver uses to get the public key of AGS, and it uses then this public key to verify the host health certificate. So
I could interject there as well.
Yeah.
What that's doing is talking to an endpoint that existed way before SQL came and made this ask of us. This is called the metadata endpoint. It's even how Hyper-V determines trust in a Host Guardian service. You have to say at some point, a human being trusts that machine. You then go to an endpoint which doesn't require any authentication. As long as you can reach it, you can get it, and it will send you back an XML document, which is the metadata that describes the keying material that this guy is using. All that's happening here is he's reusing the same code paths we used in Hyper-V to go and get the metadata that describes a trustworthy HDS.
So at this point, assuming that we have used a TPM mode, right? The client knows that the machine is healthy and has booted properly, and most importantly, the hypervisor, which is the entity that provides the isolation and guarantees the security of the enclave, is healthy and secure and hasn't been tampered with. The next step is the client driver verifies the enclave report was actually signed by this host. And then it digs into the enclave report and verifies the signature, a specific signature of the SQL DLL library that implements cryptographic operations and operations on sensitive data like range and so on. This library has a specific signature, which the client driver knows and compares, verifies that that's what is running inside the enclave. And at the end, it also verifies that the enclave, by any chance, is not running with what is called a debug mode. So you could run a VBS enclave in the debug mode. When we were developing this feature, our developers used that a lot. That's not what you want in production, because in the debug mode, anybody can actually see the enclave memory. That's only used for development purposes. So we want to make sure the enclave is not running in the debug mode. So this is all kinds of checks and the verifications we do to establish this trust between the client server, between the client application, the client driver, and the server-side enclave that is supposed to be this trusted representative, trusted extension of the client on the server side, right? The main key takeaways from what we explained regarding attestation. The two attestation modes, host key attestation, TPM attestation, use the first one to get started with the feature. There is extensive documentation. I will point you in a moment. As Dean said, it's fairly easy. You can set it up in a few minutes. TPM attestation is a little bit more time consuming.
Not so easy.
Yeah, maybe not so easy, but still reasonable.
Well, once you've done it, the point being, I think it's complex. Cryptography does get complex, but you do it once.
Right.
Once the host is up and running, I would say it's probably arguably worse for Hyper-V fabrics because they probably stand up and take down virtualization hosts far more frequently than you stand up and replace SQL hosts because they want them faster, they're moving stuff around. In your model, it's very much make it work once, and I'm kind of done. Yeah, go ahead, sir.
But if, for instance, install something on the host, then I have to recreate the signature.
So the question there is, if I installed something on the host, do I have to recreate the signature? The way that we measure things is often done with code signing certificates rather than the hash of the binary itself, because if we hash the binary, a single patch from even Microsoft will cause the hash to change. So we look at code signing certificates for the most part, such that patching won't do it. If you added a tool, an admin tool, that really depends whether or not you're enforcing code integrity policies. Code integrity policies permit certain things to run, and in the hypervisor will block anything else. Jakob and I have had this conversation ad nauseum now, and for SQL DBAs, the hypervisor enforced code integrity policy he and I have eventually agreed is nothing. So you don't enforce anything whatsoever, because the DBA's tools tend to be fairly frequently changing, and there isn't anything that we can see in terms of an attack vector that could be used anyway. So for your binary that you're adding to the box, if you patched something, or it was a third-party, say, anti-malware or something like that, you might cause the TCG log to change. You might. It's unlikely, though, if we recorded it with code signing certs, it will still wash, everything's happy. With hypervisor-enforced code integrity policy, you could break it, but given the recommendation for SQL Always Encrypted with enclaves is to have no hypervisor-enforced code integrity policy, or just a 0-1, then that shouldn't break it either. So it should be easy. Right.
So in closing, let me share where we are in terms of current status of this technology and the roadmap for the next few months or so. So as I said earlier, we are very excited about the 2019 SQL Server 2019 announcement made earlier this week, because this is the first ever public preview. In fact, there is a public preview of SQL Server 2019, which means this is also the first ever public preview of Always Encrypted with enclaves. All of you can now try this feature. Again, host key attestation mode would be the way to do that. It comes with all that functionality that I demonstrated in place encryption, rich queries. One thing that you will not, you cannot try and test in the current version is indexing. That's a very challenging problem, support for indexing on encrypted columns. We're working on it, and our desire or goal is to support it by RTM. So currently, if you try this feature, try range comparison or pattern matching, they will be done using table scans, right? So they will be fairly slow. That is one of the reasons why we currently rich queries, not in place encryption, but rich queries are disabled. You have to enable them by setting a trace flag, because we are working on a bunch of perf optimizations, including support for indexing.
Question there?
How about column store index? So that is further out. That's on our roadmap, but you may not see it in 2019 RTM. That's a major effort. We'll tackle it at some point, but probably it will take us a little bit more time.
Every time you guys hear him say roadmap,
right,
all I hear is him saying, I'm going to be contacting you soon, Dean, set up a meeting because I want something else.
Exactly.
That's all I hear. Very different interpretation of that.
All right. So right now we use VB as enclaves, and as we discussed, this is the technology that is supported in Windows Server 2019 and the new Windows clients. So your machine needs to be equipped with one of the supported OSs. In addition, you need to have a separate machine to run the attestation service. We haven't talked about it, but again, for POCs, you need just one extra machine to host AGS single node. For production, you'll have to have a failover cluster where we recommend 3 instances of AGS, right?
For your proof of concept, you could even use a virtual machine if you like. It doesn't really matter. You're just trying to get the attestation to get out of the way so that you can see what SQL does.
Okay. How many of you are using Azure SQL Database? Okay, so we may be wondering when this is coming to Azure, right? And so it is coming to Azure. We're working on it. Azure is using Intel SGX enclaves, so the work involves, among other things, porting this to Intel SGX, which we are working on. Speaking of Azure, this effort to enable Always Encrypted in SQL Server in Azure SQL Database is part of the broader effort at Microsoft that is called Azure Confidential Computing Initiative. They were at Ignite. There were a number of talks. I think there is a theater presentation by Mark Rusinovich, unfortunately happening at this time as well. But you can get a recording of the earlier session from ACC team. So what is this about? Azure Confidential Computing, it will bring to Azure customers a few components. So first of all, we are bringing SGX-equipped machines to our data centers. we're giving you an ability to provision virtual machines that run on this hardware. And we're working on the attestation service for SGX enclaves in Azure. In addition, in the top tier on the screen, you will get an SDK from Microsoft called Open Enclave SDK so that you can develop your own applications taking advantage of the enclave technologies, right? In addition to that, you will see more and more Microsoft services and products, including Azure services, that use enclave technologies to protect data in use, or maybe to protect intellectual property of code that you deploy to Azure. Azure SQL database, always encrypted with enclave, is one example of that, but we have similar efforts in the blockchain space, in multi-party computations and machine learning, right? In addition to that, we invest a lot of effort in identifying any potential vulnerabilities in the enclave platform and addressing these issues proactively as soon as we can. Okay, so in closing, I'd like to encourage you to try it, to really try to deploy it, try Always Encrypted with secure enclaves. There is extensive documentation that we have published early this week. I have a blog, and I'm going to publish fairly regularly articles on interesting aspects of Always Encrypted with enclaves. But the main ask here is, if this is something that you think is applicable to your scenarios, if this is something that your organizations can benefit from, we would love to hear from you directly. We would love to engage with you in POCs, evaluation projects, help you get going with this feature and learn it from you, right? So I think one of the main takeaways, or the main takeaway from this presentation, from this session, is that this is a very challenging area, right? A very challenging problem to solve. But we believe we are on the right path to solve it, but we need your help. We need to learn from you about your scenarios, get your feedback to make sure that we ship in the next milestone, which is SQL Server 2019, and in subsequent milestones, meet your requirements is something that will benefit you and your scenarios. Any questions? Okay, we'll stay after the session. I will be also in the SQL booth if you have any follow-up questions, all right?
Thanks for listening, everyone.
Thank you so much.